Every one of these aircraft was approved. Someone signed off, and people died because of it. These aren't accidents, they're decisions. In the 10th place, the de Havilland Comet entered service as the world's first commercial jet airliner in 1952, promising a new era of speed and altitude. But beneath its modern lines, a fatal miscalculation hid in plain sight. Engineers chose square windows for a sleek look, overlooking how sharp corners would triple stress loads with every pressurization cycle, about 30 times per flight. The result? Microscopic cracks radiated from window corners, growing invisibly until the fuselage failed. Within 2 years, 3 comets broke apart mid-air over Calcutta, Elba, and Naples, killing 77 people. Investigators at the Royal Aircraft Establishment confirmed the flaw by pressurizing a stripped Comet hull in a water tank, watching it rupture at the window. Certification minutes from 1951 show regulators approved the design despite incomplete fatigue data. Britain's jet age leadership evaporated overnight as the Comet's grounding handed the future to Boeing and set the first global standard for fatigue testing. The tragedy began a pattern: known flaws, deferred fixes, and lives lost to decisions made far from the cockpit. Number 9. The Douglas DC-10 entered commercial service in 1970, carrying a hidden risk, a cargo door design that could fail catastrophically if not latched in exactly the right sequence. In 1972, American Airlines Flight 96 lost its cargo door over Windsor, Ontario. The floor buckled, but the crew landed safely. No one died. Investigators traced the problem to a flawed latch mechanism, but instead of mandating a fix, the FAA struck a private deal with McDonnell Douglas. The so-called gentleman's agreement allowed airlines to delay installing a reinforced lock, citing an $800,000 per plane cost. 2 years later, Turkish Airlines Flight 981 suffered the same failure. The door blew out, the floor collapsed, and the crew lost control. All 346 people on board died. Internal memos and FAA transcripts show the risk was known, but economic calculations overruled safety until the worst single aircraft disaster of its era forced a belated regulatory change. 8th place, the Lockheed F-104 Starfighter became a symbol of how political influence and financial incentives can override technical reality. Originally designed as a high-altitude interceptor for the US Air Force, the F-104 was pushed onto West Germany in the early 1960s, despite clear evidence that its razor-thin wings and extreme wing loading made it dangerously unforgiving at low altitude. Lockheed's own engineering data showed the Starfighter was ill-suited for the Luftwaffe's new role as a low-level nuclear strike platform. Yet, in 1965 and 1966, Lockheed paid over $1 million in bribes to German officials, as detailed in Justice Department filings, to secure the sale. The result was catastrophic. 292 of Germany's 916 F-104s were lost in accidents, and 116 pilots died, nearly 27% of the fleet destroyed. The press called it the Widowmaker, the Widowmaker. Internal Bundeswehr statistics show that between February 1965 and July 1966, a Starfighter was lost every 2 weeks. Each crash was not just a function of pilot error or bad weather, but a direct outcome of a procurement process that ignored the aircraft's documented limitations in pursuit of alliance politics and corporate profit. Number 7. The Boeing 737 MAX stands as a modern echo of past failures, only this time the shortcut was software. When Boeing redesigned the 737 to fit larger, more fuel-efficient engines, the new placement caused the nose to pitch up in certain flight conditions. Instead of re-engineering the airframe or retraining pilots, Boeing introduced MCAS, a software system designed to push the nose down automatically. MCAS depended on a single angle of attack sensor, with no backup. Internal emails from 2016 and 2017 reveal engineers and test pilots raising alarms about the lack of redundancy and the decision to keep MCAS details out of pilot manuals. In 2018 and 2019, Lion Air Flight 610 and Ethiopian Airlines Flight 302 crashed after MCAS activated repeatedly due to faulty sensor readings. Both crews fought for control, but the system forced the aircraft into unrecoverable dives. In total, 346 people died before regulators grounded the MAX worldwide. FAA certification documents show that Boeing's own staff handled much of the safety analysis, while cost and schedule pressures drove the decision to conceal MCAS's true function. The result was not an accident, but a calculated risk, one that cost hundreds of lives. Number 6. The Mitsubishi A6M0 entered the Pacific War as a marvel of engineering, light, fast, and with a range of 2,800 kilometers. It outflew every Allied fighter in 1940, but that performance came at a deadly cost. In February 1940, a Navy Technical Committee memo spelled out the decision. Armor plating and self-sealing fuel tanks would cut speed by 10% and reduce range. To maintain maneuverability and reach, the Zero's designers approved an airframe with almost no protection for its pilots or fuel. Diaries from veteran pilots describe the consequences. Single incendiary rounds from enemy fighters could ignite the tanks, and cockpit armor was absent by design. Once Allied tactics exploited this weakness, losses surged. More than 1,800 airframes were destroyed in combat, and over 500 elite aviators were killed. Many burned alive in their cockpits. The Zero's legacy is a stark lesson in the calculus of wartime expediency, a conscious trade-off signed off by command that wiped out Japan's irreplaceable core of pilots in just 3 years. Number 5. The Lockheed Electra L-188 entered airline service in 1959 with a flaw that would turn routine flights into engineering experiments. After Braniff Flight 542 lost its wing mid-air over Texas, killing all 34 on board, investigators struggled to explain the cause. 4 months later, Northwest Orient Flight 710 suffered an identical failure, claiming 63 more lives. The pattern was clear. Wings sheared off in flight, but the underlying mechanism remained elusive. Lockheed engineers eventually traced the disaster to a phenomenon called propeller-induced harmonic resonance. Under certain conditions, the engine mounts flexed just enough to let vibrations build up, reaching a frequency that shook the wing structure apart. Rather than ground the fleet or mandate a redesign, the FAA imposed a 250-knot speed limit, allowing the Electra to keep flying with a known, potentially deadly defect. The official NTSB report in 1961 acknowledged the risk, and FAA Airworthiness Directive 710303 kept speed restrictions in place for decades. 92 people died before a permanent fix was developed, a stark example of regulators choosing operational limits over structural safety. Number 4. The Royal Aircraft Factory. BE-9 stands as one of the earliest examples of design choices putting crew in direct mortal danger. In 1915, British engineers faced the challenge of giving a machine gunner an unobstructed field of fire. Their answer was to mount a nacelle for the gunner nearly a metre ahead of the propeller, entirely exposed at the front of the biplane. This configuration blocked any chance for the gunner to communicate with the pilot or escape in an emergency. Worse, if the aircraft nosed over on landing, a common event on muddy Western Front airfields, the spinning propeller would slice through the nacelle with the gunner trapped inside. Royal Flying Corps logs and letters from the National Archives show pilots and mechanics repeatedly warning the War Office of the BE-9's deadly flaw. A formal complaint was filed in 1915, but the aircraft remained in frontline service. 12 gunners died before the BE-9 was finally withdrawn in 1917, not because of a safety fix, but because better aircraft arrived. The BE-9 story is a stark reminder. From the earliest days of military aviation, known hazards were too often accepted as the cost of doing business, with human lives left to pay the bill. Coming to the top three, the Convair B-58 Hustler stands as a stark example of Cold War priorities overriding crew survival. Introduced in 1960 as the world's first operational supersonic bomber, the B-58 was a symbol of American technological might, capable of flying at twice the speed of sound and delivering nuclear weapons deep into enemy territory. But this prestige came with a deadly price. Strategic Air Command documents from 1963 reveal a formal acceptance of a 22% loss rate, meaning nearly 1 in 4 Hustlers was expected to crash in peacetime operations. The Air Force's own records show that out of 78 B-58s built, 26 were lost in accidents, resulting in the deaths of 67 crew members. Many of these crashes were traced to flight control system failures and structural fatigue at high speeds, including a notorious hydraulic crack that could develop at Mach 2. Internal NTSB reports and SAC memos make clear that these risks were documented, understood, and deemed acceptable in the pursuit of strategic image. The B-58's legacy is not just its speed or design, but the policy-level willingness to sacrifice aircrews in service of national prestige, a calculation that set a chilling precedent for how much loss was tolerable if the mission demanded it. In second place, the Northrop YB-49 Flying Wing stands as a warning from the dawn of jet-age ambition. First flown in 1947, the YB-49 promised unmatched efficiency and futuristic design. No tail, no fuselage, just a vast swept wing. But beneath the surface, the aircraft was a handful. Wind tunnel data and test pilot debriefs from 1948 detail persistent yaw instability and a tendency to enter uncontrollable oscillations at high altitude. The absence of vertical fins left the YB-49 with no natural directional stability. Pilots, including Robert Cardenas, repeatedly logged warnings about how the aircraft would rotate backward in a deep stall, especially near Mach 0.9. In June 1948, Captain Glenn Edwards and his crew took the YB-49 up for a stall recovery test. The aircraft entered a deep stall, spun, and broke apart mid-air, killing all 5 on board. The Air Force cancelled the program in 1949, recognizing that the flying wing's instability was unmanageable with the technology of the time. No stability augmentation system existed to save it. The YB-49's fate foreshadowed a lesson that would echo into the jetliner era. Radical designs demand equally radical solutions for control. Without them, even the boldest vision is just a disaster waiting to happen. And finally, in first place, the McDonnell Douglas MD-11 remains a chilling case of a modern jet certified with a flaw that regulators and manufacturers never fully addressed. The MD-11 entered service in 1990, built with a horizontal stabilizer about 15% smaller than its predecessor. This design choice, made for fuel efficiency and range, left the aircraft inherently pitch unstable, especially during landing. To compensate, engineers relied on a computer-controlled trim system, but its software logic could create sudden nose-up or nose-down oscillations, leaving pilots fighting the controls at the worst possible moment. Between 1999 and 2009, 3 high-profile crashes, China Airlines Flight 642 in Hong Kong, FedEx Flight 14 in Newark, and FedEx Flight 80 in Narita, shared the same pattern: hard landings, violent bounces, and the aircraft flipping inverted. 8 people died, and more than 150 were injured in these accidents alone. The NTSB's 2000 report called for urgent software and training changes, and in Recommendation 03-8902 questioned whether the MD-11 should have ever been certified for passenger service. Yet no mandatory airworthiness directive was issued. Airlines kept flying the MD-11, pilots were told to be more careful, and the design's instability remains on the record, a final, unresolved warning about what happens when regulatory inertia outweighs the cost of a fix. Across all 10 cases, a single pattern emerges. Fatal flaws were documented, debated, and then signed off because cost, speed, or national pride outweighed warnings. Each disaster is not just an engineering failure, but an institutional choice. Approving an aircraft means deciding whose risks are acceptable and whose lives are expendable.